if we want to find a horizontal asymptote, what do we do to find a horizontal asymptote?
You do the stuff where x approaches infinity and then you divide by the highest degree.
All right, so all the ones before we've done this, right? We did the limit as x approaches infinity of the function 9x squared plus 2 inside a square root for this one over 4x plus 3, right? That's how we were finding our horizontal asymptotes, where limits as x approached infinity. So if x is approaching infinity, that means we're plugging in very, very large numbers for x, which tells us what about the 2 and the 3? As x gets very, very large, what can you tell me about the 2 and the 3?
They become negligible.
Yeah, they become very, very insignificant, very, very small, right? In comparison to, let's say I'm plugging in, you know, a 1 followed by a billion zeros and then squaring it and multiplying it by 9, that plus 2 is effectively nothing, right? So we can sort of just say those are going to go towards 0 as x gets very, very large. And rewrite this as the limit as x approaches infinity of the square root of 9x squared over just 4x. Now, what's the square root of 9x squared?
3x.
Everybody likes to say 3x, but not quite. Not always. So we're going to go in and we're going to look at, suppose x is equal to 2. What's the square root of 2 squared? Or we'll just say what's the square root of x squared? It equals the square root of 4, which is 2, right? Came out to be x, true? But what if x is negative 2? What's the square root of x squared? It's the square root of 4 again, right? Which is now 2. So does the square root of x squared always just equal x?
No, it's absolute
plus
value.
or minus x.
Right. Yeah, the square root, it's either the plus or the minus depending on what we have. And the way we define the square root of x squared is it's actually defined as the absolute value of x. And that takes into account, well, the absolute value of x is x, right? If x is greater than or equal to 0, and the absolute value of x is negative x if x is less than 0. True? That was like our definition of absolute value that we talked about the other day. And so that works perfectly for all of these square roots. Everybody good with that?
Yep.
Okay, cool. So what is the square root of 9x squared?
Absolute value of 3x.
Absolute value of 3x. All right, cool. So now, as we go towards positive infinity, what can you tell me about the thing inside that absolute value? It is always going to be positive, isn't it? Right, if x is going towards infinity, 3x is going to be positive.
Yes.
Yeah, so if I'm taking the absolute value of something as positive, it should stay exactly the same. So the limit as x approaches infinity of 3x over 4x. We'll note that when we plug in the infinity, what do we get there? We get infinity over infinity. Infinity over infinity, just like 0 over 0, is indeterminate, which means we got to do some extra work, which just means we're going to cancel out the x's and get the limit as x approaches infinity of 3/4. And what is the limit as x approaches infinity of 3/4?
3/4.
That's 3/4, right? And limit of a constant is a constant. So we have a horizontal asymptote of y equals 3/4. Everybody okay with that or no? Everybody okay with that or no?
Yeah.
Yes.
Okay, now there's a problem. What do we have? We had 9x squared plus 3, right? Is that what it was? 2? Plus 2. Okay, over 4x plus 3. Was that what the 3 was? So y equals 3/4. Okay, so there's my function. It's crossed through y equals 3/4, which is fine. And then it's coming up here and approaching this asymptote. True? It certainly looks like it's approaching that asymptote from below, correct? Do you all agree? I mean, I zoom in a little and you can see that red line is getting closer and closer and closer to that blue line, right? It's getting very close to it?
Yes.
Yes.
Okay, cool. But what about on the left-hand side over here? What about all of this? Is this going to get closer and closer to this value of y equals 3/4, you think?
It looks more like it approaches negative 3/4.
It certainly does, right? It looks more like it's approaching negative 3/4. Let's just for fun put in negative 3/4. Oh, geez, that looks perfect. It looks like it's just coming right up against that line y equals negative 3/4, which would tell me that in one direction, now put it back up there, y equals 3/4. I have a horizontal asymptote, right? To the right, it's y equals 3/4, but it looks like to the left, it's negative 3/4. True? Did you guys agree with that?
Yeah.
Yeah, so none of the ones that we've dealt with previously had any sort of difference between what was happening to the right and to the left. But this function has different horizontal asymptotes to the right and to the left. And so anytime we're looking for a horizontal asymptote of something that is not just a rational function, like all the ones we did before, right? A polynomial over a polynomial, because a polynomial over a polynomial will always have the same horizontal asymptotes. Anytime you have a different function, you have to also look at the limit as x approaches negative infinity of that function to make sure that there's not something happening that is different in the other direction. Good or no? Conceptually okay with that?
Yeah.
So if we simplify the 9x squared plus 2 or the 4x plus 3 back down to this absolute value of 3x over 4x, now what's the value or what's the sign of 3x? 3x is
Negative.
negative infinity. 3x is now negative, which tells me that this, when I take its absolute value, needs to become a negative 3x over 4x. Or a limit as x approaches negative infinity, if we cancel the x's, of negative 3/4, which gives us negative 3/4. So we have y equals negative 3/4 to the left, and we have y equals 3/4 to the right. So two different horizontal asymptotes in the opposite directions. Good or no? Any questions there? Okay. Should we do another one similar to that, or we feel okay about that?
Another one.
All right, let's do another one of those. That sounds good. Let's look at the function y equals the, let's see, what do we want to have here? Let's have 5x minus 1 over root 4x squared plus 6. So I'll give you guys a second, see if you guys can go through and find the horizontal asymptotes of this. There are two different ones, one to the right and one to the left. So I'll give you guys about a minute or two to work on that. Ready to go. So first off, as we do the limit as x approaches infinity, 5x minus 1 over root 4x squared plus 6, We can eliminate the -1 and the 6 because they become insignificant and get a limit as x approaches infinity of 5x over absolute value 2x, which as x goes towards infinity, the absolute value of 2x just becomes 2x since x is positive. Or the limit as x approaches infinity to 5/2, which is 5/2. And if we do this to the right, I'm sorry, to the left, the limit as x approaches negative infinity of 5x minus 1 over root 4x squared plus 6. This becomes the limit as x approaches negative infinity of the 5x over absolute value of our 2x. And now that absolute value of 2x, the 2x is negative, so when we take the absolute value, we have to take the opposite of it, which gives us negative 5/2. So we have y equals 5/2 to the right, and we have y equals negative 5/2 to the left. Everybody good or no?
Good.
All right, cool. So next up, we're going to move into dealing with some exponential functions. So we're going to start with the function e to the x and e to the negative x. Before we worry about these limits, let's real quickly go back here in Desmos and just, you should all hopefully know what e to the x looks like, but just to refresh your memories if you've forgotten, it's just a simple exponential function. Has a y-intercept of 1 and gets very, very steep and gets very, very large very, very quickly as we go past x equals 0. And as we put in negative values of x, it gets very, 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 very small. Everybody good with that?
Yep.
Okay, what about if I put a negative in front of that x and I look at the function e to the negative x? What does that look like?
Is it reflected over the x-axis?
Wrong axis, but it is a reflection. It reflects over the y-axis. So it's going to just flip the other direction. So that as we put in negative values, the y values get very, very large. And as I put in larger x values, it gets very, very small, very close to 0. So e to the x and e to the negative x, right? Reflections over the y-axis. Now, using those two graphs, we should be able to determine these 4 limits. So as x goes towards infinity, what is e to the x? That should be e to the infinity, right? And what is e to a very large power?
Very, very large.
A very, very large number. So we'll say this is infinity, although technically that limit doesn't exist because it's not approaching a real number. And what about the limit as x approaches negative infinity of e to the x? Just based on our graph, as x approaches negative infinity for e to the x, that's this one. What does it look like it's approaching as we go towards negative infinity?
0.
Sure looks like it's going towards 0, right? And we should be able to, algebraically manipulate this and say this is e to the negative infinity, or 1 over e to the positive infinity, right? And 1 over e to the positive infinity, that's 1 divided by a very, very, very big number, which should be 0. Good or no? All right.
Good.
What about the limit as x approaches infinity of e to the negative x? What should that one be?
0.
Yep. Same reasoning with the e to the negative infinity right there, right? That drops down to the denominator and becomes 0 when we approach infinity for this one. Or if we looked at the graph to the right, there's a horizontal asymptote of y equals 0. And then what about this one? Last one here. Ought to be
Infinity. Infinity.
infinity. All right, so we're going to use these 4 limits that we now know the limits of, that we should just basically be able to sort of remember those based on the graphs, I hope. We're going to use those limits to help us evaluate some slightly more complicated ones for functions that we may not know exactly what the graphs will look like. So we're going to start with the limit as x approaches infinity of e to the 6 minus 2x minus 5x squared. So looking at that, there is a piece of that that you that probably makes that a function you don't know what it looks like. What piece of it makes it something you don't know what it looks like because of it? I don't know if that didn't make any sense. But what piece of that is causing this to look different than just e to the x? All of this exponent, right?
Yep.
Yeah.
Yeah.
So if that was just e to the x, or let's say it was just e to the u, we know what e to the u looks like, don't we? Just looks like e to the x, right? So what does u equal? U is 6 minus 2x minus 5x squared, right? If I want to replace that to make this e to the u, I also have to replace the x approaches infinity. So if x is approaching infinity, what is u approaching? If I plug in infinity to this, what piece of this, the 6, the 2x, or the 5x squared dominates the rest of it? Is more powerful than the rest of it.
The 5x squared.
5x squared, yeah? And so the 6 and the minus 2x are going to become insignificant. But the minus 5x squared dominates the rest. And if x is infinity, what is minus 5x squared? That ought to be negative infinity. Would you all agree with that?
Yeah.
Yes.
All right, so this then becomes the limit as u approaches negative infinity of e to the u, which is
0.
0. Exactly. Now, I don't have it up here, but what if I had made this the limit as x approaches negative infinity of e to the 6 minus 2x minus 5x squared? Couldn't we do the same thing and substitute out the u, or substitute out the 6 minus 2x minus 5x squared as a u? And what would that tell us? As x approaches negative infinity, what does u approach?
Positive infinity.
Are you sure? Again, these are dominated, right? So we're just left with negative 5x squared. And so if we square the negative infinity, that's a positive infinity, but we still have to multiply it by that negative to make it a negative infinity again. Everybody see that? And what should that come out to be?
Zero.
Yep. Which tells us that on both sides, to the left and to the right, this has horizontal asymptotes of y equals 0. And we could go in and graph this if we wanted to. We have e to the, what was it, 6 minus 2x minus 5x squared. And
We can't see
that-
Desmos.
Sorry. Yeah, and so if we graph that, we can see that to the left, it's approaching 0, and to the right, it's approaching 0. Right? Good or no?
Good.
All right. Cool. So let's move on. Let's see if you guys can take a second here and do this one on your own. So I'll give you a minute to do this one. Same concept. We're going to do the same U substitution thing. So ready? So what's the substitution that you made? Let U equal what?
X to the fourth minus 2x plus 1.
X to the fourth minus 2x plus 1. And as x approaches negative infinity, what does that tell you about U? U should be approaching
Infinity.
positive infinity, right? That x to the fourth dominates, and negative to the fourth is always going to be a positive. So we just end up with the limit as U approaches infinity of e to the U, which is infinity. Or technically it doesn't exist. Good?
Do we need to do the limit as x approaches positive infinity?
Since I wasn't specifically asking about asymptotes for this one, no. But I mean, if I did ask you about asymptotes, then yes, you would want to.
Okay.
Yeah, this one was just specifically a question about the limit, though. So.
For like writing this on like a quiz, or do you want us to say does not exist or just say infinity?
Either one would be fine. I'd take either one. I'd probably prefer the infinity though, just so that I can see that you had a general idea of what you were doing.
Okay, thank you.
All right. Last one that's exactly like this. We're going to do one more after that's similar, but if we do the substitution, I'll just do this one with you guys. U is 2 plus x cubed. And if x is going to negative infinity, what is U going towards? Should be negative infinity cubed, which will be negative infinity.
Negative infinity.
Yeah, good. So we have the limit is U approaches negative infinity of e to the U, which is
0.
0. Perfect. We all getting the idea on these? Feeling okay about it?
Yep.
All right. Last one of this general type before we move to something even less pleasant. So the limit as x approaches 0 from the right of e to the 1 over x. What do you think we should do with that one? What should we do? What do you guys think?
Should we start by plugging in the 0?
All right, plug in the 0. That's always the best thing to do to start, right? So if I plug in 0 from the right, what is that going to do for us here?
We get an undefined exponent.
Yeah, we're going to get an exponent that's undefined, which is a problem. So let's substitute out that undefined exponent. Let's let U equal 1 over x. If x is approaching 0 from the right, what is U approaching?
Infinity?
Yeah, it should be a positive infinity, right? Because we're dividing by a very small positive. A positive divided by a very small positive ought to be a positive infinity. So this becomes a limit as U approaches infinity of e to the U, which gives us infinity. Good or no? Okay. Now let's look at one that's just a little bit different. Any thoughts on what we should do? Probably just try to plug in the infinity first and see what happens. If I just plug in infinity to e to the 10x, what's e to the 10x if x is approaching infinity? That's infinity, right? And what about the minus 4 e to the 6x? That would be minus infinity, wouldn't it? And what about plus 3 e to the x? That would be plus infinity.
Yeah.
And then what about the plus 2 e to the negative 2x? What would that be?
Negative.
Plus 0.
Yeah, so this is going to negative infinity. E to the negative infinity is 0, so that becomes plus 0. And this last one becomes minus 0. So some parts of this are okay, right? 0 minus 0, that's no problem. But anytime you have this, infinity minus infinity, that is another indeterminate form. And you've got to do something to deal with it. So any thoughts or ideas on what you might do to deal with that? Which pieces of this were not a problem? The ones with negative exponents were clearly not a problem, right? Because they were zeros. Is there a way to make most of the rest of this have negative exponents?
Yeah, you could rewrite the terms so they
How
could
so?
have like, for example, 3e to the x you could write as 1 over 3e to the negative x.
All right, well, that 3 would actually stay in the
Oh,
new
yeah,
one. But yeah,
sorry.
3 over e to the negative x, like that. Okay, so let's think about what happens if I plug in infinity to this now. What happens if I plug in infinity to this? I end up with 3 over e to the negative infinity, which is
0. So
well, it's 3 over getting very close to 0, right? So 3 divided by a very small positive number, which still gives me infinity. So we rewrote it so it had a negative exponent, but that negative exponent, we want to have a negative exponent in the numerator, not in the denominator, because a negative exponent in the denominator still gives us that infinity value. So how could I turn those positive exponents, 6x and x and the 10x perhaps, into negative exponents that are still in the numerator, that haven't dropped below into the denominator?
Can you do u substitution where u equals negative x?
I could, but if I did a substitution where u is equal to negative x, remember that that's just going to, so that would flip all of these to negative exponents, but it would flip these two to positive, right? But if u is negative x, then if x is approaching infinity, u would be approaching negative infinity. And in that case, we'd want to have, we wouldn't want to have negative exponents, we'd want to have positive exponents. Because the negative exponents would cause a problem if we were approaching negative infinity. It's a good idea, but it doesn't end up working. All right, I'm going to try and guide you guys in the right direction here. Here is, well, let's see, let's try this. We want to make these exponents smaller, don't we? True?
True.
Okay. How can I make the exponents of something smaller if I have like a long series of different terms written out, like x squared plus x cubed plus x to the 6th, let's say? How can I make each of these terms less?
You can factor.
I can factor this out, right? I get x squared times 1 plus x to the 4th. And And that decreased all of these some, didn't it?
Yeah.
Well, what if I, instead of factoring out, let's say, the x squared, factored out the x cubed? What would the x squared have to become?
1 over x.
Yeah, 1 over x, or I'm just going to write it as x to the negative 1, but yeah, 1 over x, and then plus 1 plus x cubed. Well, what if I took out the full x to the 6th? What would the x squared become? X to the negative
4.
4 plus x to the negative 3 plus 1. So if I were to take what out of these terms and all those terms in my parentheses, what would I take out to turn everything into a negative exponent? When I had x squared plus x cubed plus x to the 6th, and I took out x to the 6th, that gave me negative exponent and negative exponent and just a constant, right? So which of them did I take out? I took out the largest power. So let's try by taking out the largest power over here. Let's factor out e to the 10x and see what happens. So if I take e to the 10x out of e to the 10x, what are you left with?
1.
1. If I take e to the 10x out of negative 4 e to the 6x, I should get negative 4 e to the negative 4x, right? 10x plus negative 4x has to equal the 6x. And what about if I take it out of the 3 e to the x? That should leave you with plus 3 e to the negative 9x.
9x.
And then the 2e to the negative 2x ought to become plus 2e to the negative 12. And then minus 9e to the negative 25x. Everybody okay with that? No?
Is there a reason why x is now approaching negative infinity?
Nope, there's not. I don't know why I did that. Maybe I just accidentally made a mark there. Who knows? It should definitely still be infinity. Thank you for catching that. So now what happens? If I plug in an infinity to e to the 10x, what do I get? E to the 10 times infinity ought to just be infinity.
Yes.
And 1 is 1, right? And what about all of these? Anything with an e to the negative x, if x is going to infinity, ought to be 0. So we end up with infinity times 1, or infinity. Any questions on that or no? All right, what about the x approaches negative infinity one? What happens if I just plug in negative infinity? What's the e to the 10x?
0.
And the e to the 6x? Still 0. And the 3e to the x? Still 0. But then the e to the negative 2x will become plus infinity. And the minus 9 e to the negative 15x will become minus infinity. And there we have again that infinity minus infinity term, which is indeterminate. So we'll factor out what? What should we factor out this time? Since we're doing negative infinity, which ones are causing the problems?
The higher degrees, right?
So the positive ones, right,
Yeah.
are all 0, but the negative exponents are all giving me these infinities minus the infinity, and it's causing the problem. So if I could get rid of the negative exponent, so let's factor out e to the negative 15x, then that should solve the problem. So I take out e to the negative 15 from e to the 10, that would have to be e to the 25. And then minus 4e to the 21 plus 3e to the 16x plus 2e to the 13x, and then minus 9. Everybody good with that or no? Not sure why I wrote that x so far down there, but what's the limit as x approaches negative infinity of e to the negative 15x? That should equal
Infinity.
infinity. And then down here, I've got 0 minus 0 plus 0 plus 0 minus 9. Negative 9 times infinity ought to be negative infinity. And so we'll note up here, infinity minus infinity plus infinity came out to be infinity, which seems like sort of makes sense, even though it didn't end up being infinity just because it was infinity minus infinity plus infinity. But down here, we had infinity minus infinity, and that ended up being negative infinity. So, some infinities are larger than other infinities, and that's just a concept that you'll have to accept for now until you get to much higher math classes. Some infinities are more or less than other infinities, and that's why infinity minus infinity is indeterminate. Any questions on those two? Or we feel okay about that? All right, let's move on and talk about natural log functions. We should, with any luck, be familiar with what the natural log function looks like, right? Natural log of x. As x approaches 0 from the right-hand side, what does natural log of x do? It drops down towards negative infinity. And as x approaches infinity, natural log of x continues to increase, albeit slowly, towards infinity. So as x goes towards infinity, ln x is infinity, but as x goes towards 0 from the right, ln x is negative infinity. Everybody good with that or no?
Yes.
Okay. We should note that natural log of x is just the inverse function of e to the x, right? Those should be a mirror image of each other over the line y equals x. Yeah. All right. Cool. So if I could just turn these into natural log of u, let's say, it should make for pretty easy limits. If u is 4x squared plus 5x minus 2, as x approaches infinity, what does u approach?
Infinity.
Should be infinity, exactly. Infinity squared times 4 is a positive infinity. The 5x and the minus 2 are dominated by the squared power. So this becomes a limit as u approaches infinity of natural log of u. And as the x values on natural log get very large, what happens to the y values? They also get large. They increase forever, albeit not that quickly. And what would happen with this bottom one? Same function, just a different limit, right? Negative infinity as opposed to positive infinity. So if I do this same substitution, u is equal to 4x squared plus 5x minus 2. As x approaches negative infinity, this time what's u approaching?
Positive infinity.
Still positive infinity again, right? Because that x squared dominates. And if you square the negative, it makes it positive. So this becomes the limit as x. The limit is u approaches infinity. A natural log u, which we already decided was infinity. Good or no?
Good.
All right. One more of these, and then we're going to talk about something else real quick, and then we'll be done for the day. So, you guys want to try this one on your own?
Yes.
All right. I'll give you about a minute or 2 minutes to work on this one. Ready, go. So with any luck, we substituted out everything inside the natural log. So u is equal to 1 over x to the 4th minus 8x. And as x approached negative infinity, what happened to let's just look at the denominator first. What about x to the 4th minus 8x? What does that approach?
Infinity.
Yeah, positive infinity. And so u then is approaching 1 over positive infinity, which would be
Negative.
would be 0, right? And to be even more specific than just 0, if it's a positive 1 and it's divided by a positive infinity, that tells you that as we approach 0, we have to be doing it from the positive side, from the right. So we would then say that this is the limit as u approaches 0 from the right of the natural log of u. And what happens to the natural log of u as we approach 0 from the right? It should go towards
Negative infinity.
negative infinity. Good or no?
Good.
All right. Any questions on anything we've done so far with limits? Okay.
So,
Yeah.
like in the case that you're talking about when there are two different horizontal asymptotes,
Uh-huh.
when it's not rational, is it always just because it's like there's a radical or something like that?
Not necessarily. So like, for example, like e to the x has a horizontal asymptote in one direction, but not in the other. So that's one thing that could have. It could have an asymptote in one direction, but not the other. Or it could have different ones in different directions, and they don't necessarily only occur when there's a square root. But there will be something other than just a basic rational function. So anytime you're asked to justify horizontal asymptotes of something that's not rational, it's not just a rational function, you got to do both sides and see what happens.
Okay, thank you.
Mm-hmm.
If it's not rational and you're still trying to find horizontal asymptotes, should you still do like both the negative infinity and the positive infinity?
If it's not rational or if it is rational?
If it's not.
Yeah, definitely. Yeah. You should always show both anyway, whether it's a rational function or not. But if it's not a rational function, you definitely got to do both. Okay. If it's asking about asymptotes, yeah. Okay. Any other questions?
Should we like memorize the like natural log graph or no?
Yeah, you should definitely know what that graph looks like. Yeah. Yeah, you should definitely know what the natural log graph looks like, what e to the x looks like, what an exponential function looks like. You should know what square root functions look like and how to shift them around a little bit, absolute value functions and how to shift them, cubics and how to shift them around. You should, there's a lot of functions that you should just kind of just know. Yeah. All right, so we're going to spend the last couple of minutes here moving into the first sort of mini application of limits that we're going to deal with. And really what we're going to be doing from here on out, the entire rest of the year, is we're going to be doing applications of limits. Although we won't necessarily always have to expressly evaluate the limit using this limit notation. We're going to find some other ways to do some of these types of problems as we move forward. So we're going to look at the first little application of the limit, which is in what we call the definition of continuity. So I know you guys know what a continuous function means, right? A continuous function is just a function that I don't pick up my pencil on, right? It just goes on, but it's just continuous. It doesn't have any breaks in it, right? I don't, nothing weird happening like that. Nothing where I like go up to an asymptote and then come back down from an asymptote or something. Okay. We know what a continuous function is. But in calculus, the idea of continuity, and specifically whether a function is continuous at a specific point, becomes very important. And so if we talk about continuity at a point, some point C, there is a very specific definition and a very specific set of things you must show to be true to prove that a function is continuous at a specific value. And those three criteria are right here, right? In order to prove that a function is continuous at C, some value C, first off, the function must be defined at C. If the function's not defined there, it's clearly not going to be continuous there. So if the function is defined there, then you move on to, does the limit exist? So there has to be a limit of the function at C as well. And if there's not, because the limits from the left and the right are different or something, perhaps, right? Or because we're approaching an asymptote, if that limit doesn't exist, then there is no continuity there. And then lastly, that limit has to equal the value of the function. So the limit at C has to equal the value of the function at C. So numbers 1 and 2 up there have to be equivalent. And so we say, if all three of these things apply at a point, that means that the function is continuous at that point. And if all three of these things apply at every single point in the domain of our function, we would say that that function is a continuous function. So if all of the points on the function in its entire domain satisfy these three criteria, it is a continuous function. So think about something simple like, a parabola, right? Y equals x squared. Pick any C value. Is the function defined there? And here's my, well, pretend it's y equals x squared. That's a little bit below it, but no matter what x value I choose, is the function always defined?
Yes.
No matter what x value I choose, does the limit exist at that value?
Yes.
Yeah, and no matter what x value I choose, does the limit equal the value of the function?
Yes.
Yeah, so therefore, this parabolic function is continuous for all real numbers C. You pick any C, it's continuous at that point. Good or no?
Good.
What about something like an absolute value function? Is every point on that defined?
Yes.
Yep. Does the limit exist at any of those values?
Yep.
Yep. And does the function's value equal the limit? Should be. So should be continuous for all real numbers. But you think about something like a rational function. Maybe it looks like this, let's say. Okay. Suppose that at x equals 0, there's an asymptote. We'd go through and say, well, is f of c defined? Is f of 0 defined? No. Right, so done. Function's not continuous at 0. It's not a continuous function for all real numbers. Easy enough?
Yeah.
Okay. All right, so last thing we're going to say then is there are three different types of specific types of discontinuities. And one of them has two different sort of subgroups in it. But the three types of discontinuities are removable, jump, and infinite discontinuities. a removable discontinuity is just a function with a hole in it, right? A place where you end up with 0 over 0 at C. Okay. So this is a removable discontinuity. And then this one with the removable discontinuity also may have an extra point plotted at C. So the function exists for all real numbers, perhaps, but it's not continuous for all real numbers because this point at C doesn't fill in that hole that we have. Everybody good with that? The removable discontinuities?
Yeah.
All right. So then we also have jump discontinuities, and a jump discontinuity is we're going along and we stop and we jump to some other value. This usually will happen with piecewise functions. And then the last one is the infinite discontinuity. This often happens with rational functions, right? But it happens whenever we get a constant divided by 0. Right? Infinite discontinuity is a vertical asymptote. So real quickly, from the criteria from the previous page on being continuous at C, right? The first criteria being the function is defined there, the second being the limit exists there, and the third being those are equal. Which does the removable discontinuity here fail? Does it fail number 1, number 2, number 3, all of the above?
Number 3 or
Yeah.
and number 2?
So so let's start at number 1. Is our function defined at C for this removable discontinuity?
No.
No. So we can immediately say this one fails number 1. It does have a limit at x equals C, but it fails number 3 also because there's no value of the function. So the value of the function can't equal the value of the limit. Everybody good with that? So once it fails 1, we don't need to bother to figure out if it fails the rest. But what about the second one? Does this one pass or fail number 1?
It passes.
Passes number 1, right? It exists at C. What about number 2? Number 2 says that the limit exists. Does the limit exist at C?
Yes.
Yeah. But does 1 and 2, does the limit and the value of the function equal each other?
No.
So this one fails number 3. What about the jump discontinuity? Does the function exist at C?
Yes.
Yeah, looks like it. Does the limit exist at C?
No.
No, because from the left and from the right, the limits are different. So we'll say this one fails number 2. And then over here, does the function exist at C? For the infinite discontinuity, does the function exist at C?
No.
No.
Nope, so it fails number 1. Good or no?
Yep.
All right, cool. We're going to pick back up tomorrow, talk a little bit about, a little bit more about continuity. And then we're going to move into the bigger application of limits that's going to be far more important to us all year long.